bit on the digital models. So the reason we need to understand what's going on for the parasitic capacitances is just because the capacitors are everywhere. When you are dealing with digital models, it's creating time delays. So that is why you need to understand what are the caps, right? So starting from one example. So this one, Miller effect, comes from this concept because it's pulling up the voltage from one side to 0 to VDD, and on the other side is from VDD to 0 at the same time. And the consequence is eventually, if you're looking from each voltage source, it seems like it's a 2C on each side. Alright, so that's the result. 0 to VDD, and this is VDD to 0, 2C and 2C. Okay, so understanding this model will enable analysis for the transistors. So why is this? We have notes. You can look at the notes from last Friday, I believe. The Friday? I forgot, but the last lecture, okay? And so by looking at the transistors, especially inverter, VDD, it has all these caps. It's because of the gate oxide. So caps like this is how we model it. And you have to be able to identify which capacitors have Miller effect. So Miller effect means the actual input capacitance is bigger than its physical capacitance because of Miller effect. So what is the Miller effect? Refer to the notes from last lecture, okay? So because of the Miller effect, we are seeing a bigger input capacitance compared to the real physical capacitance existing underneath the gate. So this is how we model it. You know, if there's no Miller effect, just in theory, these capacitors are basically a half. So this is a half of the COX, so another half of COX. So half COX, half COX. However, because of Miller effect, these two caps have Miller effect. So actually, they are contributing. They are contributing one COX. It's 2 times half COX. Same to this one. It's COX instead of half COX. Okay. Eventually, the input capacitance by looking into the gate of the inverter becomes 1 COX plus another is half COX. So you have a question: why these two capacitors don't have a Miller effect? It's because this is tied to VDD permanently, right? This is whenever this is oscillating, this is not changing. Same to this one. This is tied to ground, so it's not changing. So these two caps don't have Miller effect. They are the same as their physical capacitance, which is if you split the gate oxide into 2 halves, they are equivalent to 2 capacitors. This is one half of COX on the top. All right, but the bottom one is getting double because of the Miller effect. Right. So if you're looking into it, the overall input capacitance for the inverter becomes. So it's a C in for the inverter becomes at the 3 halves of COX P. P, this is N. Okay, that's the overall input capacitance for the inverter. If there's no load, and you are getting another Miller effect capacitor, which is COX as well. Okay, the COX P here, CUX N at the output. Okay, so this is in the input terminal. This is at the output terminal. And assuming that there's no output capacitor, if I connect the output capacitor over here, and I tell you this is 5 picofarads, I'm asking you, what is the overall output capacitance? So we're looking at the output, this node. Since we already modeled these two capacitors as CUXP and CUXN, so we are not looking at anything else. This is at the output. So it becomes CUXN plus CUXP plus 5 picofarads. That's the load resistor, CL. Right? If the final exam it asks you to draw the RC model of the cap of this guy, it has input, VDD. That's the input, okay? And the gate. So the gate doesn't have a direct connection to the outside, to the output. It's because the gates are gate oxide. It's not like a PNP transistor has a direct connection. There's no connection, okay? So that's why we disconnected over here. This RP is the channel resistance on the top, which is RP, and channel resistance at the bottom, which is RN. And here you do have a connection. It's because it's at the same output node. So the output node is directly connected to the channel because that's a source, that's a drain, right? The drain has a direct connection to the channel resistance. That's why the switch models the on-off voltage. And also at the same time, the modeled capacitor is also, oh sorry, it's over here. Yep. There's no mirror effect capacitor on the top because this is tied to VDD permanently, right? So they're all at this output point. So that is why at the output point, we have one cap here, one cap at the bottom, one cap at the top. And these are the capacitors that have mirror effects, which is being split from this guy. So this is the half CUX, and you are getting 2 CUX on each, one on each side. So CUXP here and CUXN here. And we're not even including the load capacitor, which is CL, 5 picofarads. That's how we model it. So that's the RC model for an inverter. Okay, if it's asking you to draw 2 or a pair of inverters, you have to draw another one following the first one, which is pretty simple, just duplicating that, right? It's asking you to analyze the time delay at the output. So in that case, what you need to do is input is not getting involved in any of the time analysis because they're looking at the output node, but we still draw it here, okay? And here's the output CUX. All right, so that's the first inverter, and then you got a second one. So for the second one, the input capacitor on the top is what? 3/2 of CUXP, right? Gate disconnected. That's the output caps. This is equivalent to 2 capacitors, two inverters, and this node is basically this node. All right, if it's asking you the time delay to be analyzed at this point, what are the capacitors getting involved? What are the capacitors getting involved? 4, right? This is 4. So this point has a direct connection to the output capacitors from the first inverter, and also it has a direct connection because these are inputs. It's serving as an input. Has a direct connection to the input capacitors, the second inverter as well. So the Cin becomes 5 halves of COXP plus COXN, right? That's the overall capacitance at this node. I got here, 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 and here. H shape. And if it's asking to calculate TPLH, what is TPLH? Propagation delay from low to high, right? So low to high, which resistor is getting involved? Low to high means something getting put up, right? Going up. So which resistor is getting involved? Yeah. Jesus. Scarred me. I was thinking, oh, should we cancel the final exam? Joking. 0.7 RP in, right? I shouldn't say C in, C total probably. C total, which is the capacitor as its node, right? The C total, 0.7 RP, the channel resistance of the PMOS times the total capacitance at this node, right? So TPHL is what? High to low, which is the NMOS getting involved, 0.7 Rn times C total, same capacitance. Doesn't matter TPHL, TPLH, it's always the same capacitance. The only thing that changed is the channel resistance, because sometimes it's being put up, sometimes it's being put down, right? So the final exam is, I put a 2 hours, I think, over there, but I think it should be 90 minutes. And closed book, closed notes, calculator is allowed. You can bring a calculator. Scratch paper is allowed, but no cheat sheet. Okay. Any question on this? RC models. Another example for a dynamic power analysis. If there's a inverter is driving a cap, right? And I say this is like 5 nanofarads. Okay? And VDD is 5 volts. And here's the pulse function. I have done this for so many times, running electric VLSI simulations, so I'm assuming that you guys know what are the arguments in this pulse function, right? So what's the first one? Low voltage, high voltage, time delay, rising edge, falling edge, on time, and period. What is the time delay here? What is the time delay? That determines when you want to start this series of pulses. It's not a time delay for the circuits, right? It's just when you want to start it. You put a 0, which means it's going to start right away. Okay? It's basically just giving you either this or this, right? It's a time delay. So rising edge, falling edge, on time, period. So can you tell the frequency from these arguments? Yes, of course, you can tell the frequency. And to calculate the power consumption for digital circuits, we use equation derived from this, right? So we first find out the average current, because these are pulses, as there's no like DC current. So we are using an average current, which is total charges divided by the time for one period. And charges is basically VDD times the capacitance divided by T. And so P, dynamic average power, that's what's called. What's that called? That's what we care about. It's not really the concept of average power we calculated from the circuit one, what we learned in circuit one. But anyway, this is how we calculate it. So this is VDD times IAVG, which is VDD squared times C times F. So F is the frequency of this guy, right? So you can easily find out the power, dynamic power consumption for the circuit. As the digital circuits, we want to reduce the VDD with the power supply of the digital circuits, right? You see, you have probably noticed 180 nanometer technology we have been using. The transistor's name is called PMOS 3, right? PMOS 3. And that's the ones that are using relatively higher voltage from technology. So the lowest voltage you can use for 180 is actually 1.8. But if you're using 500 nanometer technologies, the C5 we have been using for the electric VLSI, the VDDs are 5. And if you compare the VDD, it's already significantly less than the C5. And that's why we want to use a smart technology, because it's reducing the VDD, and so eventually it's reducing the power consumption. All right. And for capacitance, definitely we know that for a smaller area of the gate, we are getting smaller capacitance. So smaller transistors will give you smaller capacitance. But reducing VDD, reducing capacitance, and you are running this faster, but eventually it's giving the same power consumption, but you are running it faster. Okay, that's the advantage of using smaller technologies. Okay. For capacitance, it's not giving you any of the parameters for the cap, for the COX in the transistor of the transistors. This 5 nanofarads load capacitance will dominate the output, because if you have a 5 nanofarad, and even though there are some parasitic capacitors like 5 femtofarads, you don't really care. You don't have to get that involved in the calculation, because it's way larger than this, like 1,000,000 times larger. So you can ignore it, right? You only need to use the load capacitance for the calculation. It happens a lot. Body effect. For NMOS, that's a P sub. Okay, so we need a well tap, even though there's no physical well, but the P sub, the whole sub, the wafer is considered as a well. It's called P well. All right, so you need a well tap in order to make the connection to the well. Okay, so P plus is a P sub well tap, and you want to short this one to the lowest potential of the circuit, because you never want to forward bias the little diode over here. There's a parasitic diode over here. Why is that? So because whenever you are trying to turn on this NMOS, you add a positive voltage drop from the gate to source, right? That the VGS has to be larger than VTHN in order to turn it on. So how do you turn it on? You are actually attracting, so this voltage source is attracting electrons to form a channel underneath the gate. So you got electrons over here, all right? So the thing is, whenever you got a forward biased diode from the well to this node. You can see if it's forward biased, which means you got higher potential at the anode of the diode and lower potential at the cathode of the diode, which means there will be a current flow. So current is going to flow in here. It's injecting holes to the channel. It's going to cancel all these electrons. So this voltage source has been working so hard to make this, to attract all these electrons to turn on the channel, right? And this guy, this parasitic diode, because the body effect is injecting holes into the channel to cancel these generated electrons, so which makes this source, which makes the circuit harder to be turned on. So the consequence is your threshold voltage will increase because it takes a higher voltage of the VGS to turn on the channel, since some of them are getting canceled by this parasitic diode because of body effect. All right? And that is why we always need a well tap, and we need to tie the well tap to a certain voltage node. For the NMOS, we tie it to ground. Okay. For the PMOS, it's a very similar concept. Okay, you need a negative voltage from gate to source in the PMOS in order to attract holes. So the PMOS channel, they have holes in the channel, okay? And because of the little p-n junction here, the parasitic diode here, it's a p and n, right? It's a p and n. If you do not tie this to VDD, if you do not do that, and the N terminal's voltage will be lower at some point, and the P plus will be a higher voltage compared to N plus, and will forward bias the diode. So what's going to happen is all these holes will be sent to the N plus, so the channel is losing holes. It takes a higher voltage of the VSG to attract more holes. So the consequences is what? It's increasing the threshold voltage as well. So VTHP will increase. And these are called body effect. And that is why we need the well taps. And we need to tie the well taps to a certain voltages. For PMOS, it's going to be VDD. For NMOS, it's going to be ground. Is that clear? If I tell you it's going to be down the final, it's going to be down the final, okay? Seriously. Any questions on this? For stick diagrams, I think you should run a summary on the paper by yourself. Like 3 PMOSs in parallel, how do we deal with it? 3, right? Okay. What about 4? Four is like this. Five in parallel. 2, 3, 4, 5, 6. You need 6 nodes. Right. And also De Morgan's law, you have y equals a b plus cd, right? And because of the AOI logic, it's and or inverse. So eventually it's getting inverted. And that is why we need the two bars on the top. So eventually just leave one bar eventually, and then we can draw a schematic from that logic equation with a bar on the top, right? So we add two bars on top first, and because of De Morgan's law, we can do a, b, splitting the bar and change the sign. And do one more step. Yeah, I think you can start drawing schematic from here, right? Or you can combine them if you prefer that way, which is also fine. Okay, but that's the method we use to converting a logic equation into a schematic and then state diagram eventually. Any questions on this? I think we spent like 2 weeks on this kind of layout drawing. It's very important for manually laying out circuits. How many of you have started the Innovus, I think the lab 12 or lab something? Not too new. It's good for students, also good for myself. All right. It's hard to say no to a 300K job, right? You can understand that. Don't tell other people, Dr. Lee will leave in 2 years. It's hard. I was wanting to find a R1 institution, and so I can mentor graduate students. I even got an offer a few years ago, but I didn't go. Doesn't make a big difference, you know. The only thing makes a difference is the 300K stuff. I mean, with all the grants money and everything else, I think Florida's college is really good right now. It just it moved to CU Boulder. It's not a big change at all, but more pressure. So I actually hate it. So for a charge pump like this, all right, this one should be shorted to here. Okay. It's going to ask you what's the voltage ranges at this point, A, and what's the voltage ranges at this point, B and Y. So at the very first step, when this one pulls down to ground, it pulls down a VDD to this plate. Oh, VDD minus VTHN to this plate. Thank you. It will come back. So this generates a high voltage for a charge pump. Okay, it's basically a charge pump as well. So it's going to ask you the voltage range at this point, the VDD to VTHN, right? VDD to VTHN. VDD to from VDD minus VTHN to 2 VDD minus VTHN. Okay. However, after the first cycle, the second, the third, and all the following cycles, because of the gate voltage here is getting bigger. Oh, the voltage here is getting bigger. So this voltage is applied to the gate here. So actually this gate voltage is bigger than VDD. So in that case, the entire VDD here can be passed to this plate. You can analyze every single step by yourself, but eventually the range here will become VDD to VDD. Same to this node. So your job here is, let's just assume we know that these 2 points will be will swing from VDD to VDD. Given that, can you find out the range here? What's the voltage range here at this point? The way to do that is, I won't show you the entire solution here, but I'm going to just tell you how to analyze it. So when this is 0, right, or at least it's pulling down to 0 at this point, and this one is going up to 1, right, because there's an inverter in the middle. So if this is pushing, and the voltage here becomes 2 VDD. Why? Because in the previous cycle, when it was pulling, it pulls the VDD to this plate. So after that pulling, it already has a VDD across it. So when it's pushing 1 VDD to it, it's adding the voltage to 2 VDD. If this is 2 VDD, this is 0. Okay, so 0 will turn on what? Which one? Okay, someone, right? And eventually give you an output at something. Okay? Run the same analysis for 1, 0, and look at the outputs. What are they? That's the first question. Ranges. Second, which one has a separate P well? And how do you connect the body to the P well? Where do we want to connect the body to? Okay, for that PMOS. Which one requires a separate P well? Oh, N well, I'm sorry. So this PMOS requires a separate N well. Why? Because this point can reach 2 VDD, and that's going to be a problem. Why is that? For the rest of the circuit, you have a lot of PMOSes. So for all the rest of PMOSes, the N plus or the N well is shorted to VDD. Okay? And then you got another PMOS. If you short it to the same, if you connect, let it share the same N well for this PMOS, this P plus can go up to 2 VDD. So eventually it's forming a diode, 4 biased diode, because it's 2 VDD here and VDD here. It's forming a 4 biased diode, even though it's pretty long, but it's actually forming a diode. It's going to 4 bias the diode here. That's a P plus. That's a P plus. So how do you deal with that? Remember when you are doing the layouts, you have, that's a very quick quiz question. So PMOSes are put on the top, are placed on the top. And so these are called what? These ones. N-type, right? PMOS and N-well is N-type. That's a PMOS. That's another PMOS. Even though we didn't do that, but actually all these are interconnected. So basically they share, even though they don't share the same N-well, we should have done that, but I don't think we did that in our ALU layout. So after you finished all the layouts, you should actually draw a pure N-well layer to cover all the PMOSes. Okay, that's what we should do, but we didn't, we didn't do that. The thing is, the reason for that is we have all the N taps are interconnected. So even though they are not in the same well, but the N well taps are interconnected. It's pretty much equivalent. It's not as good as you do both, right? So you can put them in the same N well and just have they share the same N taps. That's perfect. That's a standard way to do things. However, if you don't do that, they are still shorted together. Okay, if you short this one to VDD, if even you don't have this universal N well pure layer, the N well of this guy, they have their N wells, right? The N well of these PMOSes are also shorted to the same VDD. However, for this case, we don't want to even do that. We want to disconnect. So first, no universal N well, right? Second, disconnect from here, disconnected. And that's how you generate a separate N well for this PMOS. So this is what you want to do for this one, okay? Could you label TR? It's really simple, okay? TR, T4, TPHL, TPLH in this diagram. Just mark it, draw a cursor, label it, at which voltage. Refer to the notes from last lecture. Okay, the answer is over there directly. You only need to spend a few minutes on this question, right? I think this is making this really reasonable because the final exam is on Thursday. So I'm basically telling you everything that will be on the final exam. If you don't study it, that's not my fault. A lot of students didn't get perfect score on the quiz for the R2R DAC, and there will be a problem. Unfortunately, there will be a problem on that. It's going to ask you to run the Thevenin's circuit, show all the steps, and find out VL because the DAC is the analog output. Okay, there's another question. Another one. Star ADC algorithm. The state diagrams. Okay. C5 layers. So definitely no new things, right? Just review the quizzes and homework assignments and lecture notes. Should cover every single thing that I'm gonna put on the final. DC sweep of an inverter, right? Higher width to low ratio will give you a shift to the left or to the right. Okay, this has been on the quiz for a few times. Charge pump. So voltages at different nodes. That's everything about the final.
So do you have an outline now?
Nope. "12 problems, 90 minutes on Thursday, starting from 2:30. So 90 minutes will be 4, right? Any other questions? What's that?
So do we have to come in for the final exam time? That's scheduled?
Oh, no, that's next week, right? No, it's just Thursday. Thursday this week.
Going back to like the mirror effect with the inverter.
Miller.
Mirror.
Sorry.
For the TPLH and the TPHL,
Uh-huh.
the TP low to high is calculated with the PMOS resistance,
Hmm?
and then N for the NMOS resistance is for PHL.
Yes.
Okay.
Is it gonna be here or is it gonna be in the lab?
Yeah, I don't know if there's a class schedule in the classroom. I think here's better. If here's not available, we'll do it in the lab. Otherwise, we'll come here. Yeah, just next door is easy. Okay, so from the lectures and final exams and everything, you can tell I'm not really giving a lot of workload on the finals and the exams and quizzes, not just for this class, but also for embedded. So instead, I'm trying to let you guys do a lot of hands-on stuff, because this is basically whatever during the interviews they are going to ask, or in industry you are going to use, right? And no matter what, you don't like either, I can tell. It's just heavy workload, the same, right? But I think they're same pain, but just pick up the more useful pain, to take, I think. So finals will be easy. Whatever I just talked about will be on the final, and hopefully you guys can take the time to work on your Innovus, right? Innovus cadence and 180 and the 45. So 45 for Innovus and 180 for the inverter layout. I can extend the deadline if it's necessary, but I do hope you guys can finish all these tasks. Any questions on anything? No? All right. Have a good week.
Are we meeting on Wednesday? Are we gonna meet on Wednesday?
Meeting on Wednesday? No, I don't think I plan on anything. Just work on the assignments. See here, no lecture. I'll be in the lab, help the assignments.